Welcome to the state of Puebla in central Mexico. In the distance you can see two high mountain peaks. The one on the left is the dormant volcano Sierra Negra, on top of which sits Mexico's most ambitious science project, the Large Millimeter Telescope Alfonso Serrano, or the LMT. My name is Dr. David Hughes, and I am the director of the LMT. Here we are on the road, climbing up the side of the volcano which leads to the site of the LMT. This location was chosen because the meteorological conditions at this altitude are ideal for astronomical observations at millimeter wavelengths. The LMT is a binational project between the Mexican Science and Technology Council, CONACYT, and the University of Massachusetts at Amherst. The telescope bears the name of the founding visionary scientist and Mexican astrophysicist Alfonso Serrano Pérez Grobas. With a primary reflector diameter of 50 meters, the LMT is the largest steerable single-dish telescope in the world, conducting astronomical observations at a wavelength of 1 millimeter. The LMT is capable of observing the furthest, coldest reaches of the universe, capturing photons that have traveled billions of light years. Analyzing these photons helps us understand phenomena like the birth of stars and galaxies, the nature of black holes, and the origins of the universe, including the Big Bang. We have just walked into the control room of the telescope, 25 meters above the ground. And here we see teams of engineers and scientists that work day and night, operating the telescope and monitoring the observations. Now, we have moved upstairs to the scientific instrument room, directly below the huge primary reflector. You can see the apex hole in the primary reflector rotating into view, and the multiple mirrors that focus the photons towards the different scientific instruments. Mexican engineers are working with a group of visiting Japanese scientists who are installing a new instrument for the LMT, a spectrometer that will detect molecular gas in distant galaxies in the very early universe. Moving up even further, we are now inside the steel structure of the 50-meter diameter antenna. A team of engineers conducts constant maintenance work here to keep the antenna in an optimal working condition. Radiation from astronomical objects at millimeter wavelengths is reflected from the panels and directed towards the secondary mirror above you, and then down to the tertiary mirror in the instrument room below us. The LMT is involved in a project called the Event Horizon Telescope, or EHT. The EHT uses a worldwide network of 9 millimeter wavelength telescopes whose goal is to capture the very first image of a supermassive black hole. Once a year, the EHT conducts simultaneous observations to create a synthetic telescope the size of the Earth. The radiation that each of the 9 telescopes receive from the black hole is synchronized using an atomic clock. Here we are inside the central concrete cone of the LMT, where the atomic clock, using a hydrogen maser, is encased in this crate. This clock uses the vibration of atoms to keep time with a precision of nanoseconds per day. The 50-meter diameter large millimeter telescope is now an important scientific infrastructure in astronomy and astrophysics research. LMT observations will help to advance theories and provide solutions to some of the biggest questions about the nature of the universe, its past and its future. We hope you enjoyed the trip, and we invite you to follow our work and the quest to prove a prediction of Einstein's theory of general relativity and photograph the shadow, the event horizon, of a supermassive black hole.